welcome to another lecture in the series of Advanced Material and Construction. And today we're going to talk about animate matter, living matter, biological matter, all of which talking about our relation with the biological world and the way we incorporate it into architecture. So last time we ended up with introducing the notion of biological composites. We talked about composite materials, this combination between two types of elements, fibers and matrix mainly, and we ended up mentioning that it takes upon structures that we find in nature, that is biological composite. So we have this parallel between natural fibers such as collagen or cellulose, for example, and carbon fiber, and the way these construct in combination with other materials, a material with performance that exceeds the combination of both. We call it 1 + 1 = 3, and this is exactly the way it works in nature. What is incredible in nature is actually that all this variety, the incredible performance that we see around us, the multiple variations that we see, the difference between a tree or an insect or an animal or our bones, all this, as we consider the natural world or living material, is actually composed of very few types of building block, basic building blocks. And these basic building blocks are actually fibers. So mainly categorized in four families. That would be cellulose for wood, collagen for our bones, chitin for insects and arthropods, and mainly silk for spider. In addition to the incredible richness and variety that we have on the visible side of colors and textures and shapes, what is mostly incredible that only these four types of material actually gives us the whole variety of performance and behavior of these materials that we see around us in the natural world. For example, if we see this Ashby map of toughness and stiffness, well, you see the natural materials mapped are all across the board. They are populating this graph all across, from the most flexible material to the most stiff material, and again, tough material and brittle material as well. How does this work? How does these only four elements constitute this rich variety of performance? Well, the secret is its internal structure or internal architecture of the material. If we take, for example, the bone, we see that his structure is hierarchical. We can trace the structure of the bone all the way from the collagen molecules constituting at different levels of hierarchy, the fibrils, and thereafter the bone itself, which also has two types, as we see here, the porous element and the dense element. Let's have a deeper look inside and understand how these elements contribute to the performance of the bone. Now, we want our bone to be stiff, right? We don't want it to deform. We don't want it to be flexible when there is load that is put upon it. At the same time, we would not like it to be very brittle. We don't want it to break easily. So if we get hurt, we want the bone to be able actually to dissipate this energy and not break immediately. That is, to have high toughness. If you remember, this is this area below the graph mapping the energy amount that is needed to bring the material to failure. So between these two somewhat contradictory performance criteria, the structure of the bone and the multiple level is what contributes and brings the bone to its full performance. So it starts with the basic building blocks, the molecules that are very small, and this minute size is actually what contributes to its strength. That is a low level of flaws. The flaws are minimal relative to the size of the tiniest element. But on the upper level, that is the level B that we see here, we see already the composite construction of the material. So we have these collagen molecules that are bonded together with a mineral matrix. This mineral matrix is what gives the material its stiffness. Another level up, we have a non-collagenous material which actually bonds these elements together, these composite elements together to form fibrils. And this non-collagenous material is actually what assures that this material will be tough, that we will not break too easily, because this allows for some flexibility within the material itself. So this constructs these fibrils, and then another level up, we have the lamellar construction of these fibril, lamellar arrangement, and their orientation is what assures the optimal performance of the material with the direction of the load. You can see in the image of the bone itself that we have two types of arrangement. Some are highly dense, and that's the outer layer that we have in our bone, and the other, the internal parts, are porous. That is to assure performance with minimal material, because we don't want our bones to add non-necessary weight to our overall body, for example. Finally, there are also aeons, which are these types of canals that runs through our bones, and that is actually the performance of our bones as an organ. In quite a similar way as we have the collagen composite that is composing our bones, we have the chitin fibers that compose the insect's cuticles. So again, a composite material, fibers, and protein matrix in this case, constructed hierarchically all the way up from the molecules forming these fibrils that together form the fibers. And here they form this helicoidal structure, pretty much like plywood with varying orientation. This is actually what assures the material toughness. This is why it's not easy to break the insect cuticle. This is vital for the insects. That's the protective barrier. So at the same time, this material is very efficient. It's not heavy, but it is protective, it is rigid, and it's not easy to break. It has high fracture toughness. So this is thanks to this hierarchical construction. But not only that, it also has to behave or to assure quite a lot of function. This is something that we have a lot of difficulties to do in our engineered system. Imagine a material or a system that would at the same time be the skin and the bones, because it's not only the protective barrier of the insects keeping inside what should be inside, like minerals or water, and outside what should be kept outside, like enemies, like pathogen, like chemicals that would harm the insect. So this is the skin or the protective layer of the insect, but it is also the bones, the system that assures or holds inside all the soft organs. There are no additional elements, structural elements inside the insect's body. So skin and bone at the same time, assuring a high fracture energy, and so that is toughness and rigidity. Well, at the same time, this rigid material is also what enables the movement of the insect and its ability to move around, to jump. So in our engineered world, somewhat contradictory element, and to end up, not only that, but this is also a sensorial organ, pretty much like our skin. This is the way the insects get information from the environment. So a large surface sensitive to the modalities that are around, the different frequencies that is sensed around, giving information to what is going on. So a large sensory organ of the element giving information and vital information for its survival. We move to another family of natural material, which is based on the silk fiber, that is the spider silk. There is a huge fascination with spider silk and spider web. It's very architectural, and this is the reason why Thomas Saraceno, as an architect, he is exploring and researching these structures for almost a decade now. This is from a very large exhibition held in Paris a few years ago, where he was displaying his research together with scientists to understand the complex different structures of the spider web. And this fascination is not only scientific, but also translated into architectural space in these installations that try to capture the principle, the three-dimensional organization in space. So these principles, and bring it to an architectural installation, not only suggesting another structure, but also a sensorial experience. So here in this installation, the crowd is going around, and by slight friction of these cables, a sound is produced. fascination with the spider web actually starts with the material itself, again performing based on the same principle of its internal structure by hierarchy. Starting again with the tiniest molecules that at the upper level constitute a nanocomposite, a protein nanocomposite, combined of two different materials, as we always have. One of them would be these beta sheets that are stiff. This is what assures the material strength. And the matrix that is flexible, this is what assures its extensibility, its ability to elongate. So these particles, these comprise the fibrils on a higher level. And the fibrils, in their turn, they have the ability, the elements within the fibrils have the ability to open up and close back again. And this is what assures the material toughness. When load is applied, material does not break, but opens up and closes back again in a flexible way. These fibrils constitute the fiber and packed densely within this sleeve. This is what actually constitutes the spider fiber. And the roughness of these fibrils and their friction inside the fiber itself, this is actually what assures the strength and the roughness of the silk material itself and its overall performance. Compared to other materials, such as nylon, Kevlar, and even steel, we can see the mechanical performance of this material and why everybody is so interested in this material. So its elongation at break, that is how much you could apply tensile force on the material before it breaks, how much it would elongate. Now it could go up to 50% of elongation, 50% of its original length. In addition, before breaking, compare it to steel, that is a ductile material, it's only 8%. So this is quite significant. And at the same time, the tensile strength of the material is 5 times stronger than steel. Now, of course, you have to remember this is relative strength, that is with relation to its density, to its weight. So its relative strength is 5 times stronger than that of steel, an order of magnitude higher than nylon. These extreme mechanical properties of the spider-silk material, along with other properties like shape memory, light transmittance, ability to absorb water, flexibility, and more, these stand at the basis of this global search for artificial fibers that are inspired, that mimic the spider silk. So all across the world, also in Israel, we have startups that are trying synthetically to produce this spider silk. And there are various ways and approaches to produce spider silk, from biomineralization to coating of fibers, and also the construction of nanocomposite material that we have here in this example. That's a collaboration in Cambridge between architecture and chemistry. This is why I chose this example. So this is, again, highly relevant also for us as architecture. This is a supramolecular fiber, as they call it, and its special characteristic, its damping property, its ability to dissipate energy, to absorb the energy. You see here the supramolecular fiber is compared first to spider silk, to natural spider silk, and it even goes above and beyond the natural spider silk. And if you compare it to nylon, for example, it is way above as well. So high properties of energy dissipation. Finally, the fourth category of biological fiber, which is cellulose, that construct the plants, the trees, and everything that grows around us. Again, on the same principle of internal structure that is based on hierarchy, from the tiniest molecules all the way to fibrils, fibers, and then to the plant wall itself, as we see here, the bamboo stem structure. Bamboo is at the same time very flexible. It's not easy to break, and it's very strong. And this special performance is actually due to its internal structure. You see here some analysis of this plant, of this structure. It is thanks to these rings that are very stiff, and the parts between the rings that are less stiff, more flexible, thanks to internal material organization that is not uniform. So it will be more dense in the rings, that will be in the parts in between, and also the fiber orientation that would allow this bending of the material in the longitudinal section, as well as in the cross section from outer layer to inner layer. You have varying density of the fibers and their orientation. Our interest today as architect in this material is not only as an interesting structural mechanical model, but as a material for construction itself. So taken from vernacular architecture, it is industrialized today and applied mainly for its extreme fast growth rate. This material can grow up to over 1 meter in 24 hours, over 12 meters in 50 days. This is quite incredible, and it means that it could regenerate very fast, and therefore it's highly sustainable. Now, the fact that it grows so fast also means that it can serve for other environmental purposes, such as stabilizing soil or reforestation or protection of soil against erosion. So all these purposes actually make this material highly interesting in the architectural field for sustainable application. Bamboo is actually a good example for this dual interest that we have in biological material. So on one hand, you have the model that you would like to replicate or imitate in synthetic or engineered system and materials. And on the other hand, you have the material itself and the interest in that as a material for construction or biofabrication. That is, the fabrication of material with biology as its driving force or its internal engine. Well, this is done today experimentally, mainly in different areas, from plants and animals to bacteria, algae, and fungi. And we'll start with that because this is the most well established maybe in architecture today. So when we talk about fungi, that is the mushrooms, we actually talk about mycelium. Mycelium is what is underneath the soil, what we don't see. It's not the popping up mushroom, but this web that is created underneath for its nutrition. So fungi are saprophytic by nature. That means that they nourish from the decay or dissolved organic material. So we have a substrate, decaying substrate organic, that it could be any waste, and then the mycelium spore, and together these form a natural biocomposite. So this natural biocomposite, according to the substrate that nourishes these mycelium spore, actually brings different characteristics and properties, mechanical properties, and also visual characteristics that can vary according to the material, both materials. This is an interesting comparison between the properties of expanded polystyrene or EPS boards and mycelium composites. So we see that mycelium is slightly more dense than the EPS board, and its compressive strength actually could equalize or even go beyond some types of EPS boards, depending on the density of the board actually. What is most interesting maybe is the thermal resistance of the material that goes far beyond that of the EPS board, meaning that this could be a very good insulator. The material could be also a good shock absorber, and this has been identified quite early on by the packing industry, and industrial mycelium-based packaging material is already well spread. Even IKEA has replaced styrofoam with mushroom bioplastic, that is mycelium-based composite material. Also in architecture, we see a growing interest of this material in the past decade, and just recently in the Venice Biennale, you see the Belgian pavilion with an indoor application of the material as panels. And here they actually emphasize the variation or the aesthetics of these biofabricated material, where you have just a partial control of the end result, and you have variations of tones and of texture, which makes this material very natural. An outdoor application a few years ago in the growing pavilion You see panels that are surrounding this building with quite a few characteristics that make this material highly interesting in terms of sustainability. So to start, this material is based on waste. You don't need to invest energy or resources. This material is based on waste, and it is very fast production material, only 4 days. This is what we call a low energy synthesis material, meaning that you need very few elements and low energy to fabricate the material. This is how biology works, actually. Biological material are materials with low energy synthesis. So here we have hemp waste in that case, waste from agriculture that is processed in a very simple way. Mycelium just grows on this waste in closed condition, and when it reaches a certain level, you just stop the production with artificial baking in a low temperature, about 70 degrees, and the material is ready. This was the principle also of the living, the installation of the MoMA PS1, where there was this manufacture of bricks, of mycelium bricks, for this impressive construction. And the idea was a full life cycle. So you start with the manufacturing, a factory, a natural factory of mycelium, where just in a few days you get your final product of the brick. And in the same way, this is the material that is planned for its decay, for its end of life, a full life cycle of decomposition. This material is biodegradable, everything is organic, therefore fast decomposition of the material in natural condition to start the process again. Just as we have mycelium as the driving force of this production process, we can have bacteria as the engine or the driving force for an alternative biofabrication process for cement. What is naturally taking 100 or thousands of years in natural processes such as coral reef, we have calcification of material by bacteria over decades, hundreds of years. Well, here it's speeded up in this lab process with a solution that includes the bacteria, of course, other nutrients, carbon and calcium, all this together with aggregate, recycle aggregates in that case, to have the final product or the brick as we see it here. Well, no more 28 days of curing as we know for our traditional concrete. Here, this solution is cured in a matter of days, maybe 72 hours. No more high temperature and extreme high carbon footprint of the production of cement as we know it, but rather a room temperature fabrication that is zero carbon footprint. And the switch or the focus is going from the construction site to the lab with the development of solutions and alternatives to clean up construction, to reduce the carbon footprint that we induce with our concrete all over with bacteria-built cement or biofabricated bio-cement. This has been explored in various directions in the world. You see different types of bacteria today explored for the fabrication of cementitious material, for the biofabrication, of course. And another example we see here, this is Prometheus already offering bricks or blocks, not yet structural material, but this is under development. In their solution, they not only include bacteria and aggregates, of course, but also microalgae. And together, they are working on a solution to offer structural material. Already today, their block is equivalent or even superior to other concrete blocks that we know as we know them. Thermal insulation, sound absorption, weight, etc. are here described with regards to a comparison to traditional brick elements. And recently, they have collaborated with SOM, so a strong commercial traditional architectural firm, to display or demonstrate in the Chicago Architecture Biennale the possibility of this bio block and the future prospect of biocement material in our architectural world. Algae is another source of interest for designers and researchers alike for biofabrication processes that would eventually replace the petroleum-based polymers or oils or energy resources. So why algae? Well, it is an extremely efficient source for biomass production. It converts CO2 into 75% of oxygen. It mainly requires light to grow, can grow in very harsh conditions that not require land, can use wastewater for its cultivation, so very low-cost cultivation, does not require highly specific condition, and grows very, very fast. Well, actually, it's been already introduced in the consumer product as the alternative filament, for example, for 3D printing, as you see here, commercialized already and in exhibition. For example, this collaboration of the studio developing the filament together with Zruch Design, and also an interesting collaboration in the field of fashion with fashion designer Iris van Herpen. Iris van Herpen has been continuously interested in the integration of advanced fabrication processes and also alternative materials and craftsmanship, also digital craftsmanship. And here, this is a collaboration with the studio developing the algae-based products or biopolymers for 3D printing. As fashion is the main source of pollution, one of the main sources for contamination of water, mainly in dyeing, well, it is interesting to see what is the potential of more sustainable materials in the field of fashion. In a similar process that we have biofabrication of algae that suggests alternatives to plastics, as we just saw, well, we can have also alternative to fossil fuels in biofabrication of biofuels. The same process in a photobioreactor, what is called, you have algae, a source of water that could be wastewater, and CO2 that is being transformed into oxygen thanks to a light source and a process of photosynthesis. So this energy can be harvested, and of course you also have byproducts of the process, for example, fertilizers, but the main issue is that you can harvest energy. And what you need is a light source, for example, a building's facade, where it is exposed to environmental radiation, that is sunlight. And if you have these bioreactive facade panels, well, you have microalgae in the panels that are going through the photosynthesis thanks to the exposure to light, and energy can be harvested for the direct use of the building itself. Well, this can let us imagine a future of zero carbon footprint housing where energy is directly harvested from the facade of the building that we are constructing. The benefit of using the actual biological material or engine is clear as in the source for biofabrication. But we can also use it in a more indirect way to use nature's wisdom and efficiency. The question arising at this point is whether the morphological form and function principles of nature, which have developed over 3.8 billion years of evolution, can be used for structural, functional, and ecologically efficient building structures. Well, this is actually biomimetics. This is the dual model that we showed before over the bamboo, either looking at it as a material that we could use in itself or as a model that we can learn and apply. This is an example of a bamboo serving as a model for the structural principle of this high-rise building of SOM, trying to understand how the model of flexibility and resilience of the bamboo structure could be transported into the high-rise envelope to withstand high wind load in that case. This fascination with nature starts with trying to understand and classify. We saw Ernst Haeckel before in this idea of taxonomy, of families, of trying to understand how things evolved and in what is the logic behind it. So beyond the taxonomy of Ernst Haeckel, here looking at fungi, at slime, and at algae as an example, well, beyond that, we have now the wish to innovate with this understanding, and this is biomimetics or bionics. So from natural processes and models applied all across engineering sectors, not only in lightweight construction and architecture, but also in sensors and communication, the biomechatronics and robotics, fluid dynamics, and motion. So all across engineering disciplines, this process of identifying a biological process that is of interest, then abstracting its principle, and from that building a completely newly artificial system based on this principle, the principle of biomimetics, and we'll demonstrate it here with this tubular element of composite material. The development of this technical element actually starts with a plant. It's the Dutch reed, a giant plant that could go up to 6 meters or more, very slender, and its structure is a tube, a hollow tube. And what's interesting is its cross-section. The cross-section of the stem wall that you see here on the right shows a differentiated distribution of material. That is, from the outer layer inwards, you have an increasing porosity of this layer of the stem wall. This actually resembles engineered structures, as we know, for example, the I-beam, where it assures structural height without having a full section of material, that is assuring stiffness and stability of the structure. So you see here these beams along the wall of the stem of the plant, and additionally the outer layer of this stem is undulated. You see here the red line. That means that it adds curvature to the surface and overall stiffness and stability to the plant, while also enabling some relative movement, that is the flexibility of the stem, to withstand wind loads. We can draw an analogy to a shell, a concrete shell of Pierre-Louis Ginervi, for example. This is kind of a hybrid between a beam and an arch, or a plate and a shell, if you wish, where you have main veins that have structural heights. These act actually like beams, and the rest of the shell is much thinner, so you have this porous or hollow structure of the shell that resembles pretty much the stem. And from that to the composite element, so it's a knit fiber composite that is hollow in its section, and it assures extreme stiffness and performance while being very, very light. Another structure that is porous and takes its origin from a natural model is this pavilion of the ICD and ITKE Research Institution in Stuttgart. This pavilion starts from the sea urchin. The sea urchin is an underwater creature that is actually a shell that is not only very, very light, but also very stiff and resilient. And this is transported into the world of wood. Several elements are interesting in this organism of the sea urchin. starting with a plate growth pattern and elements that are put together in fiber and joint connection in a zigzag way, as we see here. The wall of this shell is a double layered wall, and material distribution within this wall is differentiated, as we saw before. Transposed into the world of wood, it is bent according to fiber orientation, so a differentiated material distribution according to fiber orientation, and each element, each component of the structure is actually a double layered component, porous and very, very light. And elements are connected in between with this zigzag and finger joint connection, together with light fiber connection, as we will see in a moment. All is digitally fabricated, so cutting the elements as per the design, and their bending geometry is assured with these outer ribbons that are sewn onto the elements, assuring exact geometry of connection between one element and the other. And the robotic sewing that they have developed, as we see here, prepares the element for future connection and assembly in a similar way to sewing or threading between the elements. As elements are porous, they are extremely light and could be very easily manipulated during assembly, not requiring a specific or extensive machinery. Elements are threaded together, and the zigzag joint and perfect geometry assures an interlocking of the elements, so no movement and stability and stiffness, with a very light and simple connection. The shape of these components, the wooden component, is achieved by bending of a flat sheet. The active bending principle that we saw already before in the One Ocean Pavilion. Here, in a case of fiber composite elements, these lamellas that open and close and generate this form just with a very simple motion at its ends. The origin of this pavilion as well, this principle is also learned from nature, from this plant, this paradise bird plant. And you see here it has two positions, an open and closed of the flaps of the plant. The principle actually it works by a load that is applied on the tip of the plant by a bird or an insect. And from this principle learned, you see the bending mechanism, a very complex shape changing, a morphing of the surface that is achieved with a very simple pulling of this linear cable or thread. This flapping open mechanism is further applied to an engineered element of facade that could also flap open and close by a very simple linear tension applied on its tip. This is called the flectofin, also in fiber composite, generating a complex surface with very simple motion, and that could be also adaptive to the climate change and environment. From imitating a mechanism from biology or from nature, we'll go to a material or even material structure. Here, the very well-known case of the lotus leaf and the fact that it is self-cleaning. This principle of self-cleaning actually is a material property depending on its internal architecture. So you see water droplets just form giant spheres over the surface of the leaf, and water does not get infiltrated in the surface, in the membrane itself. It rolls down to the center of the leaf. This principle is relying actually on the microscopic architecture of the material.
Again, the secret is in the microscopic detail of the lotus leaf. Its surface is covered in tiny bumps, each of which is capped by a waxy layer. The caps repel water, forcing it to perch on the very tips of the microscopic bumps. Unable to reach the leaf's surface, all the water can do is roll back into a sphere. And since it's repelled by the tiny bumps, there's nothing to stop it rolling off the leaf. But even more impressive, the water drops pick up any particles of dirt on the leaf's surface and carry them off as well. So lotus leaves are always immaculately clean. A reason why they're a symbol of purity in Eastern religions.
On this principle of the lotus leaf, we have quite a few developments already. So here we see a textile. After it's woven, a substrate is applied on the fabric. It's a coating that forms, upon drying, this little microstructure, just as we saw in the structure of the lotus leaf. And these little kind of waxy microtips that are formed assure that it's not only water repellent, but also it repels dirt, so it's self-cleaning, pretty much adopting the principle, the natural principle of self-cleaning of the lotus leaf. This has been applied already to paints and coatings of various types. Here, a stucco applied to the outer surface of a building in this principle of self-cleaning, and recently also applied in the development of bioplastic. So on the left, you see the image of the pillared structure of a lotus leaf, and on the right, the microstructure of this bioplastic. The material is made of starch and cellulosic nanoparticles, so that is plant material basically, and its microstructure that we saw before assures the fact that it repels dirt, pretty much like the structure of the lotus leaf. It's tough and durable, and since it's made from plant material, well, it is biodegradable, assuring a whole cycle of a future of plastic. Advancing plastic with nature's principle of design, like self-cleaning, we have self-healing polymers that draw inspiration from our body, from the ability of our skin to heal itself. So once punctured, pretty much like an artificial skin, when cut, this polymer that is highly stretchable actually rebuilds itself. Molecules reform, rebind to create a new surface, a material that is regenerating.
In the future, we may be able to produce prosthetics and medical implants which can repair themselves inside your body. We can even produce vehicles which potentially could have self-healing properties, which could heal a crack within the vehicle before it can cause any damage to a passenger. Or buildings can be coated with a self-healing layer which will defend it from environmental conditions and damage.
In the building sector, we already have self-healing materials actually starting to get into commercial use. This is self-healing concrete. Well, actually, concrete has naturally the ability to self-heal itself. It's called autogenous self-healing mechanism. It works in several ways. First, there is a physical process. Well, in condition of water, when it's in contact with water, the cement can actually swell when some particles that were not hydrated are rehydrated fully in constant contact with water. So when you have a crack, it can fill itself. But more interesting maybe is the chemical process that can occur. And once in contact with water, calcification is triggered. Now, developments include bacteria that enhance this process. Let's see how this is done.
Superabsorbent polymers are located in the pores of the concrete matrix. When a crack appears in the concrete, it goes through the pores with superabsorbent polymers. As water enters into the crack, it is absorbed by the particle. The particle swells and blocks the crack. In a second phase, bacteria, which are able to precipitate calcium carbonate, are embedded in the concrete. These crystals are deposited in the crack, resulting in crack closure. Due to this, aggressive agents can no longer enter into the crack and the durability of the construction is improved. As the bacteria need to survive in the concrete without nutrients until the moment that the crack appears, they are added to the concrete mix in a dormant state. These dormant bacteria become active as soon as they come into contact with nutrients and water, which intrude via the crack. However, these bacteria cannot directly be added to the concrete matrix, as they would be crushed in the small concrete pores during hardening. Dormant bacteria are embedded inside concrete. A crack appears in the concrete matrix. When water enters into the crack, the bacteria become active. The bacteria convert the nutrients into calcium carbonate and repair the crack. When these bacteria are combined with the superabsorbent polymers, a very efficient way of self-healing is obtained. On the one hand, the superabsorbent polymers protect the bacteria. On the other, the water which has been taken up by the hydrogels can be used by the bacteria to precipitate calcium carbonate.
So what we do is we replace the stones for hollow spheres, which we fill with food and bacteria and add that to the concrete mixture. Here we see an example of a piece of cracked concrete. You can see the crack and even a big hole. Here you can see that the bacteria have closed the crack and even the big hole completely filled with calcium carbonate.
We've seen how we try to import to the design world principles of self-cleaning and self-healing taken from nature, but we would also very much like to import the principles of self-assembly, because in nature there is no builder or constructor to put components together into a complex structure, but rather there are principles of self-assembly. And this is exactly what Skylar Tibbets is exploring at the Media Lab, how principles of self-assembly could be applied in the design world. He starts with biomolecular structure that he is simulating here. So these structure, when they are put under strong motion, they would fall apart. But in a gentle motion, these components, the single components, would actually finally form a whole structure. And he afterwards take it up on scale of an installation, and we can see here how parameters of differentiation of material, of geometry, number of elements, their size, their attraction and polarity would actually form, finally, eventually, after a long motion, this stochastic motion as we see here, at the end it will form a holistic structure. This is actually a programmed structure, a desired shape that is programmed through the various parameters of the components. Here another example, it's in a fluidic environment, and also over time and motion, these elements that are predefined and programmed would finally put together just by attraction and their different parameters to create this specific and unique structure that was designed. Here it is a chair in this example. Richness and variety of nature is not only obtained by an assembly of components into a complex unit, but also by self-morphing. We see here flowers and leaves. They achieve their complex and beautiful morphology not through an assembly, but rather through a deformation of the membrane. This deformation of the membrane, this self-shaping process, is predefined in the material architecture. We see here the stop motion of a seed pod upon drying. So upon drying, it opens up in this opposing spiraling direction, and this shape, this spiraling shape, is actually predefined in the material internal architecture, as you see the fiber architecture here on the right. We can thereafter take this principle of material frustration and implement it in the design world, as we see here in this artwork, in a latex material that is completely shaped by self-shaping processes that are applied and learned from nature.
Matter is not always static. Matter can morph. Cells divide, leaves grow, octopuses transform, and pasta swells. Once we observe the physical world through a lens offering both temporal and spatial dimensions, we see reality itself morphing. While we strive to shape our world into solid structures, nature has mastered the art of self-morphing. But what if this effortless elegance could be harnessed for the design of our built environment? Picture a world where solids are no longer passive, but store information, perform autonomous motions, and play an active role in shaping their own future. The time has come to reconsider our relationship with the environment. Self-morphing systems could be the paradigm shift we all need to create a brighter, more adaptive, and more sustainable future.
This paradigm shift from nature to architecture, self-morphing, and material architecture will be the topic of our next lecture. See you there.